normal to get confused when working with relative concentrations, things like 10x or 20x. Basically, the number before that x is your dilution factor, your relative concentration, your x factor. And what it's saying is that if you had a 10x solution, it would be 10 times more concentrated than you wanted to use it at. So in order to make a 1x, a working solution of it, you would want to use 1/10 of the total volume. Similarly, if you had a 5x, well, now it's 5 times more concentrated than you want, and then you would use 1/5 of the total volume. These dilution factors multiply. So if you do a stepwise dilution, you do a 5x and then you do a 10x, you would have a 50x dilution. And when you're doing serial dilutions, well, then each time you're diluting by the same dilution factor, and those would multiply, but you're multiplying by the same number, so then it'll rise exponentially. So you go like x squared, x cubed, x to the fourth. And so basically there are different shortcuts that we could use to help us work with these calculations, work with these relative concentrations. And so let's go over a little more explicitly how we can do some examples with these, where these numbers come from, how we can set out serial dilutions to make sure that we have enough left over in each tube, all that good stuff. We use these stock solutions a lot in biochemistry. And so when we talk about a stock solution, that's going to be something that's more concentrated than you want to use it at. And often we like to be lazy when we can be lazy. And so we make stock solutions where we have multiples of 10 for easy mental math. So we might make 1,000x stock, and then we can say, okay, well, we need 1 mil of that per liter, or we need 1 microliter of that per milliliter, and things like this. And we also, when possible, choose a final volume that's divisible by that X factor. So for example, if we have a 6X gel loading buffer, we might prepare 6 microliters or 12 or 24 or 36. And that way we would add 6 divided by 6 is 1, or 12 divided by 6 is 2, or 24 divided by 6 is 4, or 36 divided by 6 is 6. You get the idea that basically we can use round numbers. So that's convenient. Making stock solutions is also convenient because it allows us to not have to make working solutions as often. So working solutions are the solutions that is at the concentration that we want to use it at. So at that 1x, whereas our stock concentration is going to be something like a 10x, like 1,000x, one of these things. And so by having these stock solutions, we're able to save space on our shelves. We're able to keep things at a more concentrated at a more higher concentration, which is going to prevent the growth of microorganisms. And it's going to keep us from having to make little solutions all the time and weigh out solids all the time. So stock solutions are our friends, but sometimes these calculations are not. So we're going to get into these calculations, but first I just want to make a note that we can do these calculations no matter what sort of concentration units we're in. So we're often in molarity or millimoles or micromoles, but we might also be in things like percent weight or percent weight volume, and various things like that. And so all of those would be, we can work with all of those because we're just caring about the ratio. So as long as they're in the same units, that'll work. And so you might need to do a little dimensional analysis to change your milliliters to microliters and things like this. But once they're in the same units, then this will all work out okay. So let's dive into how we work with these. So first off, let's deal with that X factor. Basically what that is your initial concentration divided by your final concentration. So hopefully you guys are all really familiar with my favorite equation, C1V1 equals C2V2, aka M1V1 equals M2V2, because we often have that concentration in molarity, though we don't always. So if we rearrange things, what we can see is that our relative concentration, or our X factor, basically that's just the C1 over the C2. Because that's saying our initial concentration is 10 times or whatever more concentrated than the final concentration. So that would be our X factor. This is also like the dilution factor when you dilute it, and relative concentration, all these things, it's all talking about that same value, that number before the X. So what you can do is you want to figure out how much of the concentrated thing you need to make a certain final volume. What you do is you just have to divide the final volume by the X factor to figure out how much of the concentrate you need. So for example, if you want a final volume of 100 milliliters, then you would add 100 divided by 10 equals 10 milliliters of a 10x stock. What if we wanted a final volume of 500 microliters? How much 10x stock would we need? Well, we just have to do 500 microliters divided by 10. And that would give us that we need 50 microliters of our 10x stock. What if we wanted that same volume, 500 microliters, but this time we're starting with the 20x stock? Well, in this case, we'd have 500 microliters divided by 20, and that would give us 25 microliters. Alternatively, we could have figured out how much of the 10x we need, and then say, okay, well, we're only going to need half of that because now we're 20x. So sometimes it's easier to do like the mental math in your head for things like a 10x or 100x, and then kind of just adjust based on that. But however works for you in order to help you do these calculations, go with it. The other type of calculation you might be doing is trying to figure out what your final volume should be if you know how much initial amount of stock you have. So basically you have some amount of your stock solution and you want to say, okay, if I were to dilute this to 1x, what would the final volume be? So if you start with, say, 10 mils of concentrate, how much would you have to dilute it to in order to get 1x? To figure this out, you need to multiply the starting volume of your concentrate by that x factor to figure out that final volume. So for this example, if we had 10 mils of our concentrate, we would dilute it 10x to 10 times 10 equals 100 milliliters. So that would be like a 10x dilution would give us that final of 1x, and we would have to increase our volume by that x factor amount of times. What if we start with 50 mils of a 10x stock? What volume would we need to dilute it to for a 1x working solution? So remember that we're going to have to increase the volume by that x factor amount. And so if we start with 50 mils, now we're going to say, okay, well, our final volume is going to be 50 times 10 is going to be 500 mils. So we need 500 mils of our total solution. So if we were to dilute it, that's our total volume, remember? So what we need to do was we'd need to add 500 minus 50 equals 450 mils of our diluent. So basically your water, your buffer, whatever that is. So you would add that much amount to your 50 mils. What if we start with 25 microliters of 20x stock? What volume would we need to dilute it to for a 1x working solution? Well, in this case, we have 25 microliters times 20. What this would give us is 500 microliters. And remember, that's our total. So to prepare, add 500 minus 25 equals 475 microliters of our diluent. And so that's how you would actually go about preparing these. Note that before you dilute it directly to that final volume, keep in mind that you might actually want to be adding other components to contribute to that. So for example, if you had, say, a 10x PBS buffer, so it's like 10 times more concentrated than you want, and then when we make a buffer, when we make a pH buffer, we're adding a bunch of other stuff in there too. So we might take that 10x solution, dilute it to 1x, but some of that dilution volume is going to be from other components. And so basically we would add all those components together, and then we would dilute it up to the final volume, taking into account everything that you have in that mixture. Another thing to note about dilution factors is that they multiply by one another if you're doing them in step dilutions. So this would be an example of a stepwise dilution, where you do one dilution and then you use some of that first dilution to make a second dilution. In this case, the dilution that you made the first dilution of, that whatever fold that was, is then going to be multiplied by whatever fold the second one was. So for example, if you had a 5x as your A fold, and then you had a 10x, what this would give you would be a 50x dilution, which would mean that you had 1/50th of the concentration of the initial. And basically, in comparison, you've gone to 50x the volume. The same holds true for serial dilutions. So a serial dilution is a series of stepwise dilutions where we're diluting a thing by the same factor each time. So we have the same dilution factor, that same number before the X. So we might be doing a twofold dilution and then another twofold dilution and then another twofold dilution and then another twofold dilution. These are really helpful because they can allow us to cover a large range of space. They keep us from having, in terms of concentration range, they keep us from having to do a bunch of fancy math. They keep us from having to pipette a really small amount of a concentrated solution into a large amount of something else. Remember that the smaller the amount that you're pipetting, the bigger little errors are in terms of, like, if you have a drop on the side of your pipette and the volume that you're pipetting is only a little drop, well, that's going to be adding a lot more than if you had like a drop in terms of a bigger volume. And so you want to avoid pipetting those really, really tiny volumes. And so one way to do this is by making those serial dilutions, or making stepwise dilutions at least. And when you're doing one of these serial dilutions, basically what's going to happen is that because you have the same dilution factor each time, that same X-fold, and because those dilution factors multiply, now what's going to happen is that you're going to be multiplying by X times X times X times X times X times X. And so those are going to be exponentially raised. And so basically you can figure out the final concentration of any tube based on knowing what dilution that you're at. So you can figure out the dilution factor as well as the concentration relative to the original. So relative to the tube before it, it's going to be constant in terms of the change, but relative to that first tube, that's where you're going to see this exponential difference. So let's talk a little bit about how we actually make serial dilutions. Typically, we start out by laying out a series of tubes. And what we're going to do is we put in buffer or water, or whatever our diluent is, into each tube. We put the same amount. And now what we're going to do is we're going to take some concentrated solution and we're going to add some amount of that to that first tube filled with buffer. We're going to mix it up and down and up and down and up and down with our pipette. And then we're going to basically take the same amount out of that tube and add it to the next tube, mix up and down and up and down and up and down and up and down, take that same amount out and transfer it to the next tube, mix up and down and up and down and up and down and up and down, and do this over and over. Each time the V2 for your first tube, for the one before, is becoming your V1, then your C2 is becoming your C1. But in each case of these cases, we're going to have that constant dilution factor. What you'll notice is that as you go, basically one of the tubes is going to be higher up. It's going to have a larger volume when you've actually added something to mix. So that V2 that you were working with, that's actually only going to be left in the final tube. And so all the other tubes are only going to have a proportion of that amount. But we can use math to figure out what proportion that is. And so we make enough of that intermediate volume. We have a big enough V2 so that our final volume is going to be enough that we want. So remember, you're taking some out of what you made each time you do a dilution. So in order to still have a desired finals volume worth left in the tube, you'll need to make extra for each of your dilutions. I think it helps to actually put some numbers about it onto things to make things make more sense in our brain. So let's calculate to make a twofold serial dilution of thing to get 100 microliters of each thing dilution. So we take our tubes and we lay them out, and how much buffer are we going to put in each tube? How much are we going to transfer to each tube? Basically, we can do a little math. We can say, okay, well, our total volume, that like intermediate volume, minus how much we take out, that's got to be equal to our diluent volume. So whatever the buffer or the water. So that means that the volume left in the tube is going to be your diluent volume. And therefore, we need to calculate so that that volume equals the amount that we want left in each of the tubes. So we want that to be our desired volume. So how do we go about actually figuring this out? Let's put some numbers on things. If we want a 100 microliter final volume, what would the diluent volume be for a 2x serial dilution? Basically, what we would say was, well, we said that the diluent volume would be your desired volume. So in this case, we would want 100 microliters. So that equals your diluent volume. And that's what you want your final volume to be. That's how much you want in each tube. Now remember, the last tube is going to have the extra, unless you pipette out of it. But basically that would be the final volume you want is going to be the volume of buffer or water you're going to have to put in each of your tubes. So we go ahead, and to each of these tubes, we would have 100 microliters, we'll just say buffer in each tube. Okay, now how much are we going to have to transfer each time? So we can do a little more math, and there are a couple ways we can do things. We can go ahead and we can find that total volume. And what we'll find is that total volume equals our desired volume divided by 1 minus 1 over the dilution factor. So for example, in our example, what we would say is, okay, so we have a 2x serial dilution. So this is telling us our dilution factor is equal to 2. And we want 100 microliters final volume. And we said that our desired volume, so that's our desired volume. And that's also equal to our diluent volume. And that's going to be equals 100 microliters. So our total volume, that volume for our V2 in those intermediates dilutions, well, what this is going to be is it's going to be our total volume equals 100 microliters divided by 1 minus 1/2. So equals 100 microliters divided by 1/2 equals 200 microliters. So we're going to have 200 microliters of each of those intermediates. Sometimes it's really helpful to figure out the total volume because you need to make sure that you're not going to overflow your tube. So if, say, you had 1 mil and you were mixing it with 1 mil, if you had 2 mils final, that wouldn't fit in your 1.8 milliliter centrifuge tube. So you need to figure out how high your volume is going to go so that you don't overflow your tubes. Now, how much are you actually going to transfer, though? There's a couple ways that you could do this. So one is that you could take that total volume, transferred volume that you could get that total volume that you just calculated, and you could subtract the desired volume because that's going to be the buffer. So what you could say was what you could do is you could just go ahead and say, okay, well, in this example, my transferred volume would be my total volume. So that would be 200 microliters minus the desired volume. So that was 100 microliters because that's how much buffer you have, remember? And that would be 100 microliters. Alternatively, we could have just kind of gone straight to the transferred volume. And so this equation looks a little scary, but basically we could find the transferred volume by multiplying the desired volume times 1 over 1 minus 1 over the dilution factor minus 1. So what this is saying is we take our 100 microliters, and now we're going to multiply it by 1 divided by 1 minus 1 of our dilution factor. So that would be our 1/2, and then minus 1. So this would be 100 microliters times 1 over 1/2. So that would be 2 minus 1, which would just be 1. So we'd end up with 100 microliters. So what we would do is now we know that this would also be 100 microliters. So we'd have 100 microliters of buffer in each tube, and then we'd pipette 100 microliters of our concentrated into that, and then mix, and then pipette 100 microliters of that into the next, and then mix, and then pipette 100 microliters of that into the next, and then mix. With each time, our intermediate volume is going to be that 200 microliters. And so when you have a 2x dilution, sometimes people talk about it as like a 1-to-1 dilution or a 1-to-2 dilution. So it gets really confusing when people talk about like 1 to this or this much to that. But basically, sometimes it's easier to work in terms of like 2x. It's clear about what it's talking about. It's 2 times more concentrated than you want. Okay, let's do another example. What if we wanted a 3x serial dilution? Well, here, our desired volume, that's still the same. So our desired volume equals 100 microliters. And that's also going to be your diluent volume. So going back to how we set this up, this would still be 100 microliters. And now we're saying, okay, how much is this? We want to find that. This is our transferred volume. So how are we going to go about this? Basically, what we can say is that our transferred volume is going to be our desired volume. So 100 microliters times 1 divided by 1 minus 1 over 3 this time. Our dilution factor is 3 minus 1. So that's going to give us 100 divided by 1 over 2/3 minus 1. And so basically that's going to be 100 times 3/2 minus 1, so 1/2 equals 50 microliters. So in this case, our transferred volume is going to be 50 microliters. So we're going to transfer 50 microliters of one into the next, mix, 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 transfer 50 microliters into the next, mix, 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 and keep doing that. A note about when you're doing this smaller dilution, you're doing a larger dilution, a larger fold, now you're going to be pipetting a smaller amount into a larger amount. And so you need to be really, really careful that you're mixing completely. So when you're doing something like a two-fold where you have one part per one part, it's really easy to mix it all really well. But when you're doing these smaller volumes into a larger volume, you're going to have to be really careful that you're actually mixing. Because remember that if you're just taking a little amount up and down in your pipette, it's not doing a very good job mixing. So finally, let's consider our 4x serial dilution. So in this case, our desired volume is still equal to that diluent volume is still equal to 100 microliters. So if we want to figure out the transferred volume, we can keep that the same. And now we're just going to have a different dilution factor. So what we'll have is 1 over our dilution factor of 4 minus 1. And basically that will give us 100 microliters times 1 over 3/4 minus 1 is going to equal 100 microliters times 4/3 minus 1 is going to equal 100 microliters times 1/3 is about 33.3 microliters. And so here, what you'd be doing is you'd be transferring 33.3 microliters into each tube. And so when you're doing something like this, you might actually want to change what your final volume is if you can, so that it's going to be something that's a round number. And so you might have wanted to do something like, say, 120 microliters of our solution. If we had 120 microliters times 1/3, well, then what that would be, we would be transferring 40 microliters each time, which would be more convenient. So sometimes you choose the volume based on what you need, and sometimes you choose the volume based on like what's convenient. But in any of these cases, make sure that you're taking into account that you're going to have to make more of those intermediates so that you're left with the final amount in each of the tubes. Sometimes you have to do stepwise dilutions before you start doing your serial dilution because you don't want to have concentrations at the high end and you just say what to span 50x to 400x, but you don't want to dilute more than 20x at a time. How we could go about doing this is basically, if we want 4 points spanning 50x to 400x, we can do a two-fold serial dilution. Because we could say 50x, and then we do a 2x, that would give us 100x. We do a 2x, and that would give us 200x. And we do a 2x, and that would give us 400x. And we'll put a volume on this. Say we want 500 microliters final of each of these. Okay, so if we have 500 microliters final, how much of our intermediates are we going to need? Well, this one's simple because we're doing a two-fold dilution. That just means it's going to be 500 microliters of our diluent. That's what we want as our final volume. And then it's going to be 500 microliters of our transferred. So our intermediate total is going to be 1 milliliter. So we need to make sure that our tube can hold at least 1 milliliter. And remember that this too is the dilution. And so we're saying that this is going to be 400 times diluted. So it's 1/400th of the concentration of our original. Okay, but how are we going to get to this 50x? So we said here we're going to have 50 microliters, or we're going to have 500 microliters buffer. And then we're going to transfer 500 microliters of our sample. And then we're going to do that again and again and again to get our serial dilution. But we still need to figure out how we're going to get this 50x. And our instructions are saying not to do more than 20x at a time because we never want to dilute a tiny amount into a big amount. Instead, it's better to do it stepwise. So how can we get to 50? Well, remember that our dilution factors are going to multiply. So maybe what we want to do is we want to do a 5x, and then maybe what we want to do is a 10x. So basically what we can say is, okay, now we need to figure out how to make that 5x and how to make that 10x dilution. So maybe what we'll say is we have some stock. And then what we're going to want to do is we'll take that stock and we're going to make a 5x dilution. And then we're going to make a 10x dilution. And what this means is that we're going to be left with a 50x total. And then this we'll use in order to start making our cereal dilution. So how are we going to make that 5x and how are we going to make that 10x? Well, what we need to do here is we can just take our final volume. So let's say that we want a final volume of a milliliter. And remember that we're going to be, that's not really our final volume because we're going to be taking some of it out. But we'll still have enough left over in the tubes if we don't need, if we only needed 500 microliters of each of them, because we'll be taking away a smaller volume. So to illustrate this, let's say, okay, if we want our 5x, we're going to need 1,000 microliters divided by 5 equals 200 microliters of our stock. And then 1,000 minus 200 microliters is going to be 800 microliters of our diluent. Then we're going to take some of that and make our 10x. But how much of it are we going to take? Basically, we need to figure that out. So for our 10x, here we say 1,000 divided by 10 is equal to 100 microliters of our 5x plus 900 microliters of our diluent. And that will give us a 50x, and then we'll take 500 microliters of that and use it, add it to 500 microliters of buffer to get our next one, to get our 100x, because we're multiplying 50 times 2, that'll give us 100x. And note that we are only taking away 200 microliters of our 5x, so this would still leave us with 800 microliters of that. And for our 10x, we're only taking away 100 microliters, so we're going to be left with 900 microliters. So we don't have the same volume in all of the tubes, but if we needed 500 microliters, we'd have to calculate out how much we could do, which we showed how we could do that by using that like 1 in the dilution factor and all that good stuff in order to make a desired final volume. And so what we care about is that we just have at least 500, especially of our 50x, because that's one of the ones that's actually part of our curve. And so again, we could have calculated how much to make it actually be equal to 500 microliters at the end. But if it's okay to have more, then why do the extra math and stay with the simple, just divide by your dilution factor. So I hope that helped you understand relative concentrations, working with them in the lab, and how they apply to when we're setting up our cereal dilutions and our stepwise dilutions. Remember that those dilution factors multiply. And when you're doing a cereal dilutions, this is also going to be multiplying. But in this case, because the dilution factor is the same, you're going to be, you can multiply these exponentially. And you can calculate the concentration and the dilution factor relative to that original tube just by knowing how many dilutions you've made.